cosine. Right, so we saw that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. And here was sort of a good justification of how we can relate the derivative of sine with cosine and vice versa, the derivative of cosine with negative sine. We can kind of see how the points where we know there's a horizontal tangent for cosine correspond to the points where negative sine is equal to 0. When cosine is decreasing, we see that negative sine is negative. When cosine is increasing, then negative sine is positive. So they really kind of do agree with each other graphically. So what I want to mostly do is focus on practicing these formulas a little bit here. And then we'll use these to get the formulas for all the other trig functions, for the derivative of tangent, the derivative of cotangent, secant, and cosecant. We can basically use these formulas that we've gotten already to get all the other derivative formulas, because essentially all the other trig functions can be written in terms of sine and cosine. So here, let's just practice these formulas for now. Again, here to remind us, the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. So if I'm looking at this first one here, finding the derivative of y equals x squared cosine x, what rule should I do here?
You do 2x, right?
Product.
Well, okay, so what rule am I going to need to use though?
The product rule.
Very good. We have a product, right? X squared times cosine x. So here, keep in mind, right, we have to use the product rule. Because these are two functions that are multiplied. So we'll take y prime equals, here I'll write out the product rule. So we're going to take the derivative of x squared and then multiply it by cosine x without taking a derivative, plus x squared times the derivative of cosine x. So doing the product rule. So this will be derivative of x squared, which is 2x, times cosine x, plus x squared times the derivative of cosine, right, which we said up here was negative sine. So it's really just 2x cosine x minus x squared sine x. Okay, so there, right, we had to be careful. We need to use the product rule. Let's look at the next one here. Notice here, this one we've got sine x minus x cosine x. This is the same thing, right? You've got x cosine x, so here you're going to do the product rule for this term also. Okay. Because you got x multiplied by cosine x, so you have a product of two functions. Okay, so let's work out this derivative here. Okay, well, it's just sine x here. So the derivative of sine x will be cosine x minus, and here I'm going to just open this up so we can do the product rule to this whole thing here. And let's see, so the derivative of x is 1 times cosine x without taking a derivative, plus x times the derivative of cosine x, which is negative sine x. So here, let's clean this up a little bit. So I've got cosine x Then here minus 1 times cosine x, so again minus cosine x. And then here I've got x times negative sine x, so that'll be negative sine x, but then there's a minus sign here that gets distributed. So that becomes plus x sine x. And then I noticed that these terms here, cosine x minus cosine x, those ones, when we combine them, will go away. So I'm just left with x times sine x. Okay. So you see here, we didn't want to forget that we need to use the product rule here, okay? What about the next one? Is there a different rule that I've got to use for the next one here? We've got y equals 1 plus sine x over 1 minus sine x. What rule do I need to think about here?
Quotient.
Good, quotient rule. Because we have a quotient, 1 plus sine x over 1 minus sine x. So here we have to use the quotient rule. And I'm just going to write out the quotient rule. So we remember it's the derivative of 1 plus sine x times 1 minus sine x without taking a derivative, minus, and then we'll take the derivative of 1 minus sine x in the denominator, times 1 plus sine x without taking a derivative, and all over the denominator squared, so 1 minus sine x squared goes in the bottom. And now let's see, so the derivative of 1 plus sine x, well, there we know sine x, the derivative is cosine x, so it'll just be cosine x times 1 minus sine x. Oops, sorry, cosine x here. Minus, and then let's see, we've got 1 minus sine x. So here 1 minus sine x will be negative cosine x when we take the derivative, because that's 1 minus sine x, so 0 would be the derivative of 1 minus cosine x, which is the derivative of sine x, so 0 minus cosine x. And then times 1 plus sine x. Okay. And then what I might do from here would be just a little bit of simplifying. If you guys notice, we could like distribute some things out and see what kind of things we can do from there. So like here, I'll distribute cosine x. And then here, minus negative, so plus cosine x here, I'll distribute another cosine x. So just did some distributing there, cosine x. And then what I notice is that the 1 minus, minus cosine x sine x plus cosine x sine x, those terms will combine and we get, they cancel. And so then I got cosine x plus cosine x is 2 cosine x left. Okay. So yeah, so these were just a little bit of practice with the formulas for sine and the formulas for the derivative of sine and cosine. Here, of course, we had to also mix in some product rule and quotient rule. And the next thing I want to think about are now ways of dealing with the other trig functions. Like we have tangent, cotangent, secant, cosecant. So all the other trig functions, how would we deal with their derivatives? And one thing to remember is that all the other trig functions can be written in terms of sine and cosine. Remember, so like, how can I write tangent in terms of sine and cosine?
Sine over cosine.
It is just sine over cosine. How about cotangent?
Cosine over sine.
Good, it's just the flipped over version, cosine over sine. How about secant?
I believe that's 1 over cosine.
Very good, 1 over cosine.
The last one should be 1 over sine.
And then 1 over sine. Very good, okay. So that means that if I write them this way, then I kind of have a way of dealing with each of these now. So for instance, now if I want to find the derivative of tangent, sorry, dx. Well, I can apply the quotient rule for the derivative of sine x over cosine x. Right, so I can work it out this way. Or if I want to take the derivative of cotangent, then I can do the derivative of cosine x over sine x, and here again you would have to use the product rule, or I'm sorry, the quotient rule. And same for these guys. If I want to take the derivative of secant x, I can do the derivative of 1 over cosine x and cosecant, and just do the derivative of 1 over sine x. And then in each of these, right, you notice that you can just apply the quotient rule to each of these. So let's actually work one of them out here. Let's work out tangent. So we know the derivative of tangent, like we wrote a second ago. Is the derivative of sine over cosine. So here again, we've got to do the quotient rule. Okay, so we'll take the derivative of sine x times cosine x without taking a derivative minus the derivative of cosine x times sine x without taking a derivative all over cosine x squared. And from here, we can just do what we know, like the derivative of sine is cosine. derivative of cosine is negative sine. So we've got cosine squared plus sine squared in the top. And well, does anything pop out to you guys? Do you guys see any way of simplifying this?
The top
The
being
top will simplify to 1.
Very good. Yeah, we know that
Oh,
sine squared plus cosine squared equals to 1, right? So let's just write this as 1 over cosine squared. Is there another way that I could write this?
cosecant? No, not cos. Yeah, cosecant to the 1.
Almost.
squared.
Well, careful, it's not cosecant.
Secant squared.
Secant squared, there you go. So it's, remember, 1 over cosine is secant. So this is secant squared.
That's what I said.
There you go. Good. So we've shown here that the derivative of tangent is secant squared. Okay. Essentially, this process would work for all the other ones. Okay, so if I want to do cotangent or cosecant or secant, you can do the same little trick, just doing some quotient rule and then simplifying it. But here's just an overview of all the other ones. So if you take the derivative of cotangent, that's negative cosecant squared. The derivative of secant is secant x tangent x. And the derivative of cosecant is negative cosecant x cotangent x. Okay, and those all you can work out using the same technique. Like for instance here, let's just do one more of these really quick. So let's do the derivative of secant. By doing the derivative of 1 over cosine. And then doing the quotient rule here, we'll take the derivative of 1, which is actually, remember, that's a constant. So since we know the derivative of a constant is equal to 0, so this is just 0, minus the derivative of cosine, which is negative sine. So we get sine x over cosine squared x. It doesn't quite look like the formula that we get here, but we can easily do a little bit of manipulating here. I can write this as 1 over cosine x times sine over cosine x. And there we see that's 1 over cosine is secant x. And then sine over cosine is tangent x. Okay, so there we have it. So that gives us this one here, right? So I encourage you guys to try doing that also with cotangent and cosecant to make sure you can see how they get these formulas here, just in case you forget. But this is it. So this is all the trig functions here. So now we can just practice some more of these formulas. But I definitely suggest if you guys don't memorize these, at least, you know, make sure you don't forget them, or always have a way of referencing them if you forget things easily. But yeah, normally I would say you guys have to memorize all these, so they're actually very easy to memorize. You notice that all the ones here on the right side all have a negative in front of them, right? So all the ones that have a cosine, cosecant, cotangent, they all have a negative. They're all negative, right? So that's an easy way to remember it, and they're all kind of similar to what we see over here on the right side, or on the left side, right? Okay, so they're not hard to memorize, but just make sure you're remembering them. If you forget, just reference the table, or make a cheat sheet with all the formulas. And let's practice this one here. Suppose I want to find the derivative of secant x cosecant x. Again, I've got a product here, secant x times cosecant x, so we're going to need to use the product rule. So let's write out the product rule. So the derivative of secant x times cosecant x plus the derivative of cosecant x times secant x. Okay, and then just remembering the formulas that we had on the previous slide. Secant x, if you guys remember, that was the one that we just worked out, was secant x tangent x. Cosecant x is actually very, well, that one actually, sorry, we're not taking derivative there. But this one here, when we're taking the derivative of cosecant x, is very similar formula to the derivative of secant x. It's just negative, and instead of secant x tangent x, it's cosecant x cotangent x. Okay, so that's it. You could probably simplify this some if you want, or if not, you can just leave it like this. Like one way you could go about simplifying it would be to just try and rewrite everything in terms of sine and cosine and see if that makes it any simpler. Like for instance here, I can write secant, that's 1 over cosine. Tangent is sine over cosine. Cosecant, that's 1 over sine. Here we got cosecant is 1 over sine. Cotangent is cosine over sine. Secant is 1 over cosine. So just right there, I kind of notice, the cosines here divide, the sines here divide. So I have 1 over cosine squared minus 1 over sine squared. Or I can write this as secant squared minus cosecant squared. So it looks a little simpler that way.
Professor?
Yes.
On the test, how do we know when we're done simplifying, like we got into your answer that you're looking for?
So I would give you full credit in the second step. If you wrote the second step, I would give you full credit right there.
Oh, awesome. Thank you.
So this is full credit answer right there. But sometimes if you're looking up your answer in the book, like you don't see the answer written this way. Like if you're looking in the back of the textbook trying to check your work, you don't see this written, but you see this written. So do you, yeah. So do you need to go further? Well, I would say take this as far as you need to get it, into the form that looks like the answer that you get in the book, so that you can kind of make sure that you can get it into a form where you can check your answer. But yeah, here just applying the rule correctly, it will give you full credit. And yeah, and actually I generally recommend on an exam at least to avoid the temptation to oversimplify or to go too far with the simplification, because there tends to be a lot of opportunity for making errors when you go too far with it. So you're better off not simplifying too much, at least on an exam. In most cases, some cases it might be necessary. But here, if it's just like find the derivative of some function, you know, I'm going to give you full credit if you just show that derivative step here where you've applied the rule. Okay. And let me see. So let's try this one here. We want to find the second derivative of y equals cosecant. Okay, so the nice thing is we already have the first derivative, right? That was the formula that we had on the previous slide. For cosecant, remember it was negative cosecant cotangent. So if I'm going to do a second derivative, notice that we're going to then have to apply the product rule, right? Do product rule for the second derivative. Okay, so let's write it out again. So negative cosecant, the derivative of that guy, times cotangent plus the derivative of cotangent times negative cosecant. So this will be, again, the derivative of negative cosecant was what we did here a second ago. So it's negative cosecant cotangent, and then times cotangent. And the derivative of cotangent, remember, is negative cosecant squared. Times negative cosecant. Okay, so just writing it out, right? We did just those rules again. This was the derivative of cosecant here. This is the derivative of cotangent here. And then just a tiny bit of simplifying. I think this one looks a little bit nicer if we multiply some of these things together. Cosecant and then cotangent, cotangent. So I'll write cosecant times cotangent squared. And then here we've got cosecant times cosecant squared, so cosecant cubed. Cosecant cubed. And let me see, could you go further with that? Maybe, maybe you could actually go a little bit further. I'll show you how. You can write cosecant squared, or sorry, factor out a cosecant, and then you got cotan squared plus cosecant squared. But yeah, other than that, I wouldn't go too much further than that. Again, you would get full credit. You would get full credit in this step here. Would be where you would get full credit if you got there. So this is just, you know, making sure you can get it into a form where you can recognize the solution that the book would give you, for instance, or if you're looking up your solution to compare it with the answer key. Okay. So that was the last example here. So so yeah, mostly just a bunch of new formulas in this section that you guys can practice and get good at. It's really just these 6 formulas actually. So getting some practice with these formulas, combining them with the other rules that we've had, like the product and the quotient rule. You know, also maybe solving for tangent lines and things like that. Okay, well, in the next section, we're going to do a couple of applications to motion problems. And actually, if we kind of think about when we first started talking about derivatives in this section, or in this chapter, in chapter 3, that was kind of like the very first thing that we thought about was this velocity problem. You know, given some object that's moving, you know, in one direction, either forward or reverse, like, or so moving just back and forth, you can think of that as like a one-dimensional motion problem. And so the question is, how do we find the velocity of that object? And that was what we were trying to think about with a derivative. Is a derivative actually gives us one way of thinking about the instantaneous velocity of an object. So we're going to go a little bit further with that idea in this section, in the next section in 3.6. Okay, so yeah, so we start by thinking about this idea of one-dimensional motion. And you know, one way to think about it is you have an object that's just moving back and forth on a number line. So it's got some location. So of course the number line has an origin at 0. But then you're imagining this object just moves back and forth along this number line. So, you know, at different points in time, it takes on different positions on this number line. So it's something that just kind of moves around on this number line. So what I think might be a good analogy for this, or a good way to think about this, you know, as a maybe an example you guys can picture is just imagine a train on a track, right? And this is a good way of visualizing one-dimensional motion, because a train on a track only has 2 directions. It either goes forward or backward, right? So that's, I think, a good way to imagine this. Or another way to imagine it is you you throw you know, a stone up into the air, or you throw a ball straight up into the air. Well, it's only going to be going straight up. It's going to then reach some maximum point, and then it's going to come back down, right? So another way is another way we can picture this is also like a free fall kind of problem. So we, you know, throw a ball straight up into the air. So it only goes up and then down. Okay, so these would be, I guess, two specific cases where you can model it with a one-dimensional motion function like this, s equals f of t. Okay, so s is our position function, right? So we can imagine now when we're talking about displacement is the change in position. Okay. Or what we see here is just the change in s. So if I'm going or waiting a change in time, right? So delta t would be our change in time. Okay, then our displacement here would be the change from f of a to f of a plus delta t. So now if we're thinking about the average velocity, then we're thinking of the change in position over the change in time, right? Which is really just the average velocity would be f of a plus delta t minus f of a over delta t. Okay, so it's the displacement, the total change in position divided by the change in time. Right? Essentially, it's the same as our average rate of change, in this case of position. So the average velocity is really the average rate of change of position. And then, of course, we can transform this like we've done with derivatives. To think about velocity, we can think about what happens here as delta t goes to 0. So the instantaneous velocity would be taking the limit as delta t goes to 0 of our average velocity. Okay, so we'll be taking the the limit as delta t goes to 0, delta s over delta t. Now, and what you guys notice, this is really just the derivative of s. So velocity is really the derivative of position, or the rate of change of position. Right, and here's the picture that we've seen back when we were coming up with the formula for the derivative. You're imagining now our tangent line is formed by taking a sequence of secant lines that get closer and closer to a tangent line. And of course, in this case, these represent average rates of change for the secant line. And they approach the instantaneous rate of change at the point P, which is our tangent line. So the average velocity, the displacement over the change in time, and then taking delta t to 0, we get the instantaneous velocity. So, right, this doesn't look too different than what we were doing back in 3.1 when we were defining the derivative as the slope of a tangent line, right? But now we're just putting it into this context where now we're thinking of it as the rate of change of our position function. So the velocity is the rate of change of our position function. Now let's practice here with an example. So let's assume a police station is located along a straight east-west freeway at noon, which we're assigning t equals 0 to be noon. A patrol car leaves the station heading east. The position function of the car s of t gives the location of the car, I should say, in miles east. I left out a word there. So east would be the positive direction and west would be the negative direction. And well, and so we can look at the graph here, right? We can kind of see how the position of the patrol car changes at different points in time. Okay. So this is now just sort of giving us a way of visualizing how the position changes over time. So let's try a few questions. How would we describe the location of the patrol car during the first 3.5 hours of the trip? So just kind of describing how the car is traveling over this period of time that we've shown in the graph here. So first of all, if I'm looking at this first portion, right, it's starting out here at location 0. So at t equals 0, which is really noon, right? The car leaves the station. What direction is it going? Is it going east or is it going west?
East.
Good, it's going east because we've decided that east is the positive direction. So that kind of makes sense here if we draw it like this, right? East would be the positive direction. West would be the negative direction, kind of agreeing with how we typically draw it on a map. Good, so yeah, it's going in the positive direction. And then it looks like he stops at a location 80 miles east. So yeah, at the time t equals 0 is when he's leaving the station and goes 80 miles east. At what time does he reach that location? What time would that be?
1 hour and 30 minutes.
Good, yeah. So when t equals 1.5, he stops there. So he stops at 1:30. It looks like he stays, his position stays there until 2 o'clock, right? And then it looks like he changes directions and goes back due east. I'm sorry, it goes back west is what I mean to say. Okay. And it looks like he's going west for, you know, the next hour and a half, right? So 1.5 hours. So notice that he actually passes the station, right? Because he passes the position at 0 and goes past the station. Goes 20 miles past the station. In the end. Okay, so if you want to imagine it here, how his position is changing. At t equals 0, he starts at the station, which we're putting here. After 1.5 hours, he's going to go to this location 80 miles east. And then he's going to hang out there for an hour, or sorry, a half hour. And then he's going to change directions and then head back west, but he's going to go 20 miles past station. Okay, so there's this time at t equals 0. Goes 80 miles this direction. That's at time 1.5. And he hangs out there for a while, and then at time t equals 2, he heads back this way and ends over here at t equals 3.5. Okay, so there's this motion that he has going back and forth. Now, what would be his displacement and the average velocity between 2 p.m. and 3 p.m.? So let's just look at 2 p.m. to 3 p.m. So that would correspond to these points here and here, right? So remember, his displacement would be change in position over that time. So think of it, it's his position at 3:30 minus, oh, sorry, 3:30. I put 3 here. 3:30 would be at the end here, right? Okay. So it would be his position at 3:30 minus his position at 2. right? Sort of like his final position minus his initial position. So his position at 3:30 we noticed was -20, meaning he's 20 miles west of the station. And then his position at 2 was at 80 miles east, so -80. So here we see it would be -100. Notice the negative sign indicates the direction. Right, so delta S here refers to the change in position from those two times, right? And the fact that it's negative here indicates the direction. In this case, indicating that it's pointing in the, that its displacement occurs in the negative direction. Okay. And then let's look at the average velocity. So remember that would be like his displacement divided by the change in time. There we had the displacement, which is what we just worked out, was -100. And then that was a total of 1.5 hours. Okay, so that's an average velocity of about 66.7 miles per hour. Okay, and again here the negative sign indicates the direction was in the negative direction. So it indicates the direction that he's traveling. So this tells us that he was going an average of 66.7 miles per hour in the west, headed west, right? Because west was the negative direction. Okay. And at what times is the instantaneous velocity greatest as the car travels east? Well, how would you describe that? What would I be looking for in the graph to find where is the instantaneous velocity the greatest?
The slopes.
Good, where the slope is the greatest. Good, right? So remember that, yeah, the instantaneous velocity refers to the slope of the tangent. Actually, notice that here, so I'm sorry, I'm going to go back a second here. When we computed the average rate of change, we were computing the slope of the secant line here that went through these 2 points, right? So now that I'm looking at the average, or sorry, the instantaneous velocity instead of the average velocity, we're looking at the point where the slope of the tangent is going to be greatest. So where is the slope of the tangent the greatest? What would you guys guess if you had to guess?
From 0.5 to 1.
It's somewhere in that region. Good. Yeah. So maybe you can pick something in between, right? Maybe, I don't know, somewhere right in the middle, right? So maybe at like
0.45.
0.75 maybe. Right, that's maybe where it looks like it's the steepest, right? So it appears to be the steepest. Somewhere around yeah, t equals 0.75, which is around 1245.